U-substitution is a method that we can use to help us find the derivative of a specific kind of complicated functions. Here's an easy one that we can do. If we let y equal the quantity 3x minus 1 squared, we don't actually need to use U-substitution in order to differentiate this. I mean, we could just multiply 3x minus 1 times 3x minus 1. We'll get 9x squared minus 6x plus 1. Then the derivative is going to be 18x minus 6. But I'm going to use this as an example so that we can be certain that we're getting the right answer. So going back to y equals 3x minus 1 squared. Notice that we have a function inside of a function, that 3x minus 1 is inside of a squared function. So what you want to do is let u be that inside function, the 3x minus 1. Then we'll be able to find the differential, du, as being 3 dx. It's going to be important to identify that information when we're using U-substitution, because our next step is to go back to that y equals 3x minus 1 squared and rewrite it in terms of u. Well, we let u be the 3x minus 1, so this is really just u squared. Heck, we can find the differential of that as well. dy is going to equal 2u du. Right? That's why we needed a u as well as a du, because our next step is going to be take those pieces of information and then plug them back into our differential so that we rewrite dy in terms of x and dx. So we saw that u was 3x minus 1 and du is 3 dx. This is the brilliance of that differential, is that we can treat it as a piece of a fraction and just divide both sides now by that dx. Then what we're left with on the left side is dy dx, which is the derivative. That's what we're looking for. On the right side, we end up with a 3 times 2 and distribute that inside. So 6 times 3x is 18x, and 6 times negative 1 is minus 6. So we find our derivative to be 18x minus 6, just like we were expecting. So just kind of to review the steps, when we come across a function that has a function inside of another function, what we're going to do is let u be the inside function, and then we'll find the differential of u. We use that u expression to rewrite y in terms of u, find the differential of y in terms of u and du. Then we resubstitute back into that differential the expressions for x and dx. Then it's just a little bit of algebra to divide that dx off, and we'll have our derivative. So let's try a few more examples. First thing I'm going to do is let u be the inside part, that pi times x to the third. Then the differential of u, we use our power rule, bring the power down. 3 times pi is 3 pi x squared dx. Right? That is an important part about the differential, is including that dx when we take the derivative of that right side. Right? Now, going back to y, we can rewrite y in terms of u. So since u was the inside function, we're going to have y is equal to the sine of u. Find the differential of y. So the derivative of sine is cosine, which means that the differential of sine u is going to be cosine of u du. Next, we convert everything back into being in terms of x's. And so dy is going to be the cosine of u, but u was pi times x to the third. And du is 3 pi x squared dx. our last step in coming up with the derivative is to divide both sides by that dx. Then we have our derivative, dy dx. Clean up what we're left with over here. So I'll just take that 3 pi x squared, put it in front of the cosine pi x to the third. And there is our derivative. Here we have y is equal to e to the 4x minus natural log of x. All right, so let's let u be the inside function. What we have is e to this power. So my inside function is going to be 4x minus natural log of absolute value of x. Then the differential, taking it term by term, is going to be 4 dx minus 1 over x dx, which, I mean, we could factor out that dx and have 4 minus 1 over x dx. So we'll go back to the beginning, rewrite y in terms of u, of e to the u, and take the differential. dy is going to equal eu du. Next, we return everything back to being in terms of x's. So we have e to the u, but u was the 4x minus natural log of absolute value of x. And du is given down here as 4 minus 1 over x dx. We finish up by dividing out that dx to get dy dx. Our derivative is e to the 4x minus natural log of absolute value of x times 4 minus 1 over x. And there's our derivative. Here's one more easy one. It looks pretty complicated, but it's easy. Y equals 3x to the 5th minus 2x to the 3rd plus cosine x, all to the 100th power. So let's let u be the inside function, that 3x to the 5th minus 2x cubed plus cosine. Then the differential is going to be 15x to the 4th minus 6x squared minus sine of x. And don't forget your dx. That's what we're going to use to rewrite y in terms of u. So since u was the inside part, we'll have u to the 100th power. Something that's much easier to find the differential of. dy is just going to be 100 times u to the 99th power du. Now that we have the differential of y, we can rewrite that in terms of x. So we know u was that inside part, the 3x to the 5th minus 2x cubed plus cosine. We'll take that to the 99th power and then multiply by the differential of u, which was 15x to the 4th minus 6x squared minus sine dx. And our last step, so I don't have to rewrite everything, is just going to be to divide both sides by that dx. So what we're left with is our derivative. All right, one last problem. This one is not an easy one because I see that we have a product inside of that natural log. But our steps are going to be the same. We still need to let u be that inside function, the x squared times e to the x. And we still need to find the differential of u. That's where it's going to get a little more difficult because we'll have to use the product rule, which was 1 d2 plus 2 d1. That was all dx's. Now we can take that information, rewrite y in terms of u. So we'll have natural log of u and find its differential. So natural log of u, that turned into 1 over u du. Next, we rewrite that in terms of x. So 1 over u, which was the x squared times e to the x, times our differential, x squared e to the x plus 2x e to the x dx. Now, when we divide by that dx to find our derivative, there is a little bit of simplifying that can happen. For instance, since I'm taking a fraction times this x squared e to the x plus 2x e to the x, that's going to become the numerator. And so I'm going to write that as a single fraction with the x squared e to the x in the denominator. And I'm also going to factor out any common factors I have, like the x and the e to the x. And what I'll be left with is just x plus 2. There's a little bit of canceling that can happen here. For instance, we can get rid of 1x, and we can get rid of the e to the x as well. So our derivative actually simplifies very nicely into x plus 2 over x. Well, that's how you use U-substitution to find the derivative of the composition of functions when we have functions inside of other functions.